Probably do some months of more local, quieter Milan meetup, more toward the local community. But for the last two times we wanted something very special. So the first guest of tonight will be a guest that was already here tonight for the
which is a consensus system that fiat currencies use. So bulletproofs are a form of zero-knowledge proof. It has nothing to do with consensus at all, but it certainly has a lot of exciting applications. So the original motivation for bulletproofs was to create something called a range proof for something called confidential transactions. So I'll spend a couple of slides on what confidential transactions are and why we care about them. So confidential transactions. Oh,
yeah,
I cut out.
No, you just have to stay directed to her.
Okay. Confidential transactions are, wow, it really varies. Are a crypto system designed primarily by Greg Maxwell in 2016, which are a way of creating Bitcoin-like transactions in which the amount on the transaction, the amounts of Bitcoins on the inputs and the outputs are completely hidden. He does this using what's called a Peterson commitment, which is a homomorphic cryptographic commitment. And what that means, the word commitment means that it binds to the value. You can't change the value once you've created such a commitment. And this word homomorphic means that you can still add them up. And so for verifiers of the blockchain, they can take all of the commitments on the transaction inputs and add those up. They will get a new commitment to however much is going into the transaction. They can take all the commitments on the output and add them up, and they'll get a commitment to the amount on the output. And all they do is check if the input amount equals the output amount, and that way they learn that the transaction balances. It doesn't create anything, it doesn't destroy anything, even though they don't know anything about the actual amounts involved. Okay? But these Peterson commitments represent amounts as integers modulo some large prime, which differently from ordinary numbers, the way that actual money works. For example, if you have, say, 2 to the 256 coins represented in this way, then to having nearly 0 coins. There's sort of this wraparound that happens near this prime number that's nearly 2 to the 256. So you can effectively represent negative values by taking something very close to the prime. Okay. Taking something very close to the prime, taking something that is just a small amount, you add them together, and they wrap around to 0. So in more conventional terms, you can say you create a transaction with no inputs, you create an output with, say, -1 coins, which is actually the prime number minus 1, another output with 1 coin. Of course, -1 plus 1 is equal to 0, so inputs equal output, that's all good. But I've created a coin out of thin air if I were to do something like this, because I didn't put any Bitcoins in, but I got a Bitcoin out, and a negative Bitcoin that I'll just throw away. So to prevent this situation, we use something called a range proof. And that prevents any numbers from coming anywhere near the magnitude of this large prime. It prevents them from ever acting like negative numbers or overflowing or doing anything else that's funny. But, as we will see, the range proofs that we used in the initial implementation of confidential transactions were not as efficient as they would need to be for a serious system on the scale that Bitcoin is. At least if we want to continue to allow anybody to join the system without spending thousands of dollars on validation hardware. So these original range proofs that we developed were, at the time, in 2016, the best range proofs for these small, like 0 to 2 to the 64 amounts that existed, but they still were not very fast. So these are the numbers here. They were about 80 bytes per bit, 5 kilobytes for 64 bits, and they would take you 4, 5, 6 milliseconds to verify one of these range proofs. And the way that these worked was conceptually very simple. What we would do is we'd take an amount that was hopefully between 0 and 2 to the 64. To prove that it was actually between 0 and 2 to the 64, we would just split it into bits. We say this is a 6-bit number, and it's very easy to see that it's a 6-bit number if you just split it into 6 bits. All you have to do is prove that these things are bits. You provide 6 things, 6 commitments to bits, and prove that each one of them is a bit. And you do this with something called a ring signature. which is a cryptographic tool that allows you to sign with one of a number of public keys. So the way that these bits are represented is such that if you have a bit, either your commitment to the bit is a public key, or the commitment to the bit minus some random curve point is a public key. And if one of those two things is true, then A, you have a bit, and B, you can produce a ring signature. And those are always both true or not true. So you can use ring signatures as proof of bit. But as a result, you need these separate ring signatures for every single bit. We can combine them with something we call Borromean ring signatures, which is a bit more technical than I want to go into. But ultimately, you still have these separate signatures on every single bit. You get these 80 bytes per bit. The more you want to prove, the more data you need, and the more work that a verifier has to do. So it works, but it's not as good as it could be. So in 2016, Jonathan Boodle, among others, Jonathan Boodle at UCL, published a paper about doing zero-knowledge arithmetic circuit proofs, just using Peterson commitments and discrete logs and public keys and all these various things that we like to play with in Bitcoin. And he found a way to do like very general kind of proofs, which is cool. And in particular, he did this by using something called an efficient inner product proof, proving that if you have two lists of numbers and you multiply each of the numbers pairwise, that you get some specified result. So this was published in 2016. Over the next year or so, he and Benedict Boons and Dan Boneh, both at Stanford, worked on extending this work to something that is bulletproof by taking the existing Boodle 2016 inner product argument, simplifying it. The original Boodle paper allowed you to split a number into like arbitrary factorizations, and then you would do these various polynomials based on the size of the different factors, and it was all like quite an event to even understand it. So we simplified this to work with only powers of 2. You're also able to make it smaller. Benedict found a way to drop it from 6 group elements per bit of what you're proving down to 2. So that's a 3 times space improvement. And more importantly, he found a way to do general zero-knowledge proofs, which is what Boodle did, but using inputs from Peterson commitments. So you could take a confidential transaction output, which is some homomorphically committed value that you're already adding up to prove the transaction is valid, and you can prove arbitrary things about these committed values without having to teach your zero-knowledge system how to deal with Peterson commitments. So to maybe try to explain how difficult that is, typically to work with Peterson commitments at all, you have to do elliptic curve arithmetic. You have to add these various commitments together, compare the added commitments, and each of these additions is actually some complicated fraction of polynomials. And so if you want to do something in a general zero-knowledge proof system with these, you have to implement all of these fractions of polynomials in your zero-knowledge proof system, which is a very expensive thing to do. There's a lot of operations that would be very slow. Bulletproofs can just take these Peterson commitment inputs and just work with them natively. It's no extra operation. You just take the Peterson commitment, you multiply that by some random scalar, and then it fits into your proof, the same as any other secret input. And I'll expand on that a little bit more, but not too much more, because I really want to explain what the performance numbers for this are for range proofs, and then also how this generalizes, because there's actually a lot of really cool stuff that you can do with these bulletproofs, because even though this was developed largely as a way to do efficient range proofs, as a result, we can actually do arbitrary computations on committed values in confidential transaction outputs, and that's a very exciting thing. And not only that, but public keys can be thought of as being Peterson commitments in a way. And so this means you can put public keys into bulletproofs and prove arbitrary things about secret keys without revealing anything about what they are. So there's some cool stuff that we can do that we'll talk about a bit more. But all of this is based on this inner product argument that Boodle and Boons developed. And this is very cool. This is a recursive argument. The way that these inner product arguments are generated is just a list of data, is that you go through a number of iterations, and each time you iterate, you halve the number of data that you're working with. So if you're producing a proof on, say, 64 bits of data, you go through one step of the proof, turn that 64 into 32, you generate 64 bytes of data. You do another step, 32 becomes 16, becomes 8, becomes 4, becomes 2, becomes 1, and after just 6 steps, you've got whatever 64 times 6 is, the amount of data that you produced, which is a very small number compared to 64. You're taking the logarithm of 64, which is 6, so 2 to the 6 equals 64. And your proof is proportional in size to that, rather than being proportional in size to the number of bits. This is already a very exciting development. It means that unlike the older range proofs, which in my last slide I mentioned became more and more expensive the more bits you have, these grow in size at least much more slowly than do the old proofs. And they grow slower the more bits you add. And so, as a consequence of this, it is possible to aggregate these range proofs. Say you're creating a transaction with very many outputs, say you've got like 10 outputs. Rather than creating a single range proof for each output, saying this output is a 64-bit number, this output is 64 bits, this output is 64 bits, and so forth, you can create one so-called aggregate range proof, proving that all 10 of them are 64 bits at once. And because of this logarithmic scaling, the resulting proof will barely be larger at all than the original proof. Specifically, I guess that if you're multiplying by 10, you're multiplying by 2, roughly 4 times, you're going to add 4 times 64 is 256 bytes. And you can see from this chart, this is, maybe you can't see from the back, but this is the number of bytes it takes to prove some number of range proofs. And on the bottom, we've got the number of range proofs that you're proving. And you can see that for most values here, I'm stuck between this like 1,000 and 2,000 byte number. So between 1 and 2 kilobytes. But my x-axis here, how many proofs I'm proving, is increasing enormously. I'm going from 0, 200, all the way up to 1,000 there. And so you can imagine, if you will, a transaction with 1,000 outputs, you could aggregate all 1,000 of those outputs into a single range proof, and the resulting proof would just be, well, it would be less than 2,000 bytes, less than 20 bytes per range. Now, this is maybe not so realistic for a blockchain transaction, for something that you would see like in a block on Elements or Monero or Mimblewimble or Grin or whatever various things use confidential transactions in the wild. But you might see this in off-chain protocols. For example, there's something called provisions, which is a proof of solvency mechanism. What this is a way for some...
Time, 1 hour, 19 minutes, 50 seconds. Total distance, 4.0 miles. Average pace, 19 minutes, 57 seconds per mile. Split pace, 20 minutes, 21 seconds per mile.
This is a paper called Provisions that was published a year or two ago that uses confidential transactions to hide the amounts and then uses some form of zero-knowledge proof to show that those amounts actually correspond to real amounts in the blockchain. If they were to instead use Bulletproofs to aggregate all of those different, all of the different range proofs on each of their outputs, you can see that they would be able to reduce the size of their proof from many gigabytes down to a number of kilobytes. Having said that, there is a reason that they might not want to aggregate so aggressively, and I'll talk about this in my next slide, which talks about the verification. So there's a very cool property of Bulletproofs that is different from the older range proofs that I think is really the most exciting thing. So the size numbers were very impressive. You saw that we stick within 2 kilobytes pretty much no matter how many proofs we're trying to aggregate. But the really exciting part is what happens when you have many proofs and you're trying to verify all of them at once. And you would do this, for example, in a blockchain context when you receive a new transaction. You want to verify a range proof on each one of the outputs, unless they've been aggregated. Or especially when you're doing an initial block download. When you're downloading a whole bunch of blocks that exist, but you haven't seen them yet because you were just joining the system or you were offline for a while or whatever. You see all these new blocks with all these new transactions, all these new range proofs, and you want to validate them all. And what happens is, so it's difficult to see on this graph, but the very first proof that you validate costs a fair bit of time, like probably something like 2-3 milliseconds, which to be clear is already less than the old range proofs. But then every additional proof after that, you can validate at the same time as the first one, using a trick called batch validation, where you essentially combine the different range proofs after the fact. They're all separate sort of randomization step to prevent them from badly interacting with each other. And then just verify them all in one shot. And when you do that, you will find that the additional range proofs only cost a couple hundred microseconds to verify. Okay, so we're going down from 5 or 6 milliseconds to a couple hundred microseconds in doing so. So this is already a tenfold improvement for each one. But it even gets better when you combine this with an aggregation feature. Okay? Because the time it takes to validate, to batch validate an aggregate range proof grows logarithmically with the size of the aggregate. And I'm trying not to be too technical, but let me show you on this graph what's going on. So this top line here is what the old borrowing signatures look like. Okay, that is the validation time. You can see this is a and this is just for how many proofs you are validating, how quickly does the validation cost grow. Okay? So then the very bottom line here is the same number, but for bulletproofs. So you can see that if you're validating a whole bunch of individual bulletproofs at once, the time it takes to validate grows much more slowly. It looks like I've got 3 seconds at the far right for 500 proofs, versus something like 100 milliseconds for bulletproofs. But then, if we look at the next line shows what if you're validating aggregates of 2 range proofs at once. So these are 2 range proofs combined into one, which is much smaller than 2 separate range proofs. And the line above that shows what if you're looking at aggregates of 4, and then aggregates of 8, and aggregates of 16, and aggregates of 32 and 64. So this next line here, the one almost to the top, that is the line for how much it costs to validate batches of 64 ranges, each aggregated into a single bulletproof. And you can see that after validating 500 proofs, it takes about half as much time to validate 64 aggregate bulletproofs. So it takes half the time to do 64 times as much work validating bulletproofs than it does to validate the old range proofs. So now at this point, at these scales, which you might see in like a proof of solvency thing, or even in a blockchain if you're doing an initial block download, we have over a 100x improvement. And this only gets better as you increase the scale. Okay, so that's really the exciting part of bulletproofs to me, is that this validation time grows so little. So that's very cool. This is just a story about range proofs. And it's interesting to see this because at some point, actually, these validation times grow so slowly that if you look at individual ranges, how long does it take to do that? It starts costing like 30, 40 microseconds, which is slower than the time, or less time than it takes to validate individual signatures. So if you're not batch validating signatures, then actually these range proofs become cheaper than the rest of the transaction, which is kind of cool. But I'm going to move on from range proofs to talk about the more general things that I mentioned earlier, which are the inner product arguments, which is really what these bulletproofs are. They're not just range proofs. They are general ways to prove knowledge of some things that multiply to some other things. And it turns out that the class of problems that you can describe as things multiplying into other things is pretty much all the problems. Okay? So any algorithm in which you know the running time beforehand, which includes anything that you might validate on a blockchain, as my colleague Russell would say, this is he would say it's either a delta zero language or a sigma zero language, but I can't remember which is which. What he would be referring to, if he said that correctly, is the fact that if you were validating a correct execution of some program, no matter how complicated and loopy and arbitrary this program might be, if all you're doing is validating a trace of its correct execution, that is very limited in scope. That will always have a runtime that you can predict beforehand. That will always be something that you could put on a blockchain in a way that you could at least bound the amount of effort that a verifier would have to extend to look at it. So you can verify any program at all. You can verify that it executed correctly in a delta zero language, which can be expressed as an arithmetic circuit. And this is the principle behind all sorts of zero knowledge systems that have been in the news over the last couple of years. Snarks is a big one. Starks is another one that's exciting from Ellie Van Stassen and others. And also this thing called ZK-Boo, which I don't think has got as much media attention as it should have, but that's a zero-knowledge system. And so Bulletproofs joined these family of various things. And so let me say a little bit about how it compares to these other things. So Snarks, I think, are the most famous zero-knowledge system, at least in the cryptocurrency space, because these are what are used in Zcash. Zcash uses these to create what they call shielded transactions, which are transactions in which rather than showing a bunch of inputs and a bunch of outputs, and saying, well, look, these inputs are existing transaction outputs that are there, I'm allowed to spend them, and these outputs are new outputs. You provide a zero knowledge proof that you are picking some outputs that previously existed, putting them into your transaction, and you're creating new ones. And Zcash does this with Snarks. Snarks are very cool. They have constant verification time. To validate a snark on a modern computer, like if you just went to go buy a laptop today, it would probably take you, I don't know, 5 or 6 milliseconds, and it doesn't grow no matter how complicated the problem being proven is, which is cool. It means that you can prove this complicated Zcash thing, and validators, the cost of validators doesn't grow very fast. But there are two big problems with snarks. One is that the time it takes to prove something grows very quickly, with the complexity of the problem being solved. And we'll see in the next slide, I'll show you how long it takes to validate a SHA-2 circuit using Bulletproofs versus validating a better adapted hash for Bulletproofs, which show that not all problems work very well in these arithmetic circuits. The proving time increases many minutes, maybe even tens of minutes, the way that Zcash is currently implemented. And a lot of their research these days is focused on finding more efficient hashes, more efficient things that they can prove in these zero-knowledge systems so that they can actually produce these proofs in a reasonable amount of time and have a system that anybody uses. Because right now, barely anybody, even on Zcash, actually uses shielded transactions because they're so expensive to produce. The other problem, which in some sense is much more serious, is that snarks have a trusted setup. The parameters of the system have to be decided in advance by somebody or some group of somebody who work together to build the parameters of the system. And they, in producing those parameters, need to compute some secret data, some so-called toxic waste, that is basically secret keys that could be used in principle to create completely false proofs. Okay, if you had the secret knowledge, then you could just mint all the Zcash that you wanted. And so the way the Zcash was set up is that there was a group of 4 or 5 people who all went to various places and did a multi-party computation together to produce the parameters of the system. And if it were possible to get the secret data from all of these participants, you could do this. You could create, just mint all the Zcash you want, and nobody would be able to tell, even in principle, no matter what you did. Just the way that the crypto is set up is that this is undetectable. So that's unfortunate. There are other systems out there that do not have this trusted setup. So two of the popular ones are these Starks and this thing called ZK-Boo. So Starks are a new research effort by Ellie Van Stassen and a number of researchers in Israel. Starks are exciting. They're an extension of something called the PCP theorem, which is an academic crypto theorem that shows that it's possible in principle to create zero-knowledge proofs of anything just using hashes and randomization and stuff without any weird crypto assumptions, not even something like the discrete logarithm assumption, which is something that's used for modern-day digital signatures. You don't even need that. You really just need to trust that it's possible for computers to generate random numbers, and then these are secure, which is cool. The original PCP theorem was kind of a mathematical existence theorem that basically gave a proof that it was possible in principle if you were willing to compute for longer than the age of the universe using more data storage than you could produce using all the atoms in the universe. You could produce such a proof, which is the kind of thing that academics get very excited about. I don't know why. So Starks take this from the realm of literally impossible to merely impractical. So it is possible to produce Starks. They take many hours, they take several gigabytes of RAM, Verification is not so fast, the proof sizes are not so small, but they exist. And I understand that you can validate Starks inside of Starks, and that's faster than just validating the first Stark, so maybe there's something there where you could keep starking enough times and then eventually it becomes efficient to verify. I don't know, I haven't explored this as much as I would like to, but regardless of how small you can get the verification time, the proving time is still very memory intensive and very time consuming. So this is not yet a practical system. VK-BOO, on the other hand, is. And I think of all the zero knowledge systems I'm aware of, I think this might be the first one that was really practical and you could use it for proving ordinary things. VK-BOO is actually very exciting. You take something called a Boolean circuit, which is something that people are probably more familiar with. It's just a bunch of logic gates, your ands and ors and nands and nots and whatnot. And you can produce a zero-knowledge proof using hashes and symmetric cryptography and random selection and various things like that. Similar security assumptions to Starks. It's not just hashes and random numbers, you also need some encryption and stuff. And the resulting proofs are very fast to generate, they're very fast to verify, but they're a bit large. Okay, they're going to be hundreds of kilobytes or maybe megabytes for non-trivial circuits. And they also don't have any native support for Peterson commitments. So if you wanted to use these for something like confidential transactions, or if you wanted to use these in a blockchain context where you already have encrypted numbers, committed numbers, then they're not the most efficient thing to use. Okay? They're fast to produce proofs for, but the proofs will be large, and the proofs will have to include a proof of all sorts of elliptic curve operations inside, which is very frustrating. It really slows down what you can do. Versus bulletproofs. Bulletproofs, like snarks, are very small in size. Bulletproofs are always a couple of kilobytes. Not always. I mean, eventually it will become as large as you want. It grows logarithmically. So if you had a circuit with 2 to 1 million gates, I mean, you can't fit such a thing in any popular theory of how large the universe is, but in principle you could do it, and then you would get a megabyte bulletproof. Snarks, on the other hand, are always 200 bytes. No matter how far beyond the limits of the universe you want to go, they will always be 200 bytes, which is cool. But they're still very small. For range proofs, they're typically less than a kilobyte. For typical circuit proofs, they're 1 to 2 kilobytes for the kind of circuits that I've been looking at. And the verification, at least for small problems, is reasonably fast. We saw in our graphs about range proofs that it grows very slowly, and that the numbers we get are practical to verify, at least for range proofs, and as we'll see also for hashes and some other cool stuff. But again, snarks have a speed. Snarks are always a constant time. They are always going to be 5, 6, 7 milliseconds. I'm not sure, I haven't benchmarked on modern hardware. The original snark paper from 2013 used whatever the state-of-the-art 2 gigahertz system was from that time, and they came out with about 10.5 milliseconds. ZK-BOO has comparable verification time to us, but just much larger proofs, and they don't support Peterson commitments. So that's where we fit in here, is that specifically in the context of confidential transactions and EC public keys, we are the fastest, smallest thing around, which is pretty cool. So, what do these numbers look like for circuits? Well, the classic benchmark here is SHA-256, which people are familiar with. This is the kind of thing where ZK-BOO shines. SHA-256 is described in terms of a whole bunch of logic gates, it's all Boolean arithmetic. But for arithmetic circuits, SHA-2 is kind of a pain to implement. It's going to wind up being 20, 30,000. And so for something like bulletproofs, or for snarks, or for other arithmetic circuit-based proof systems, it's not the best hash to use. So instead I'm going to compare this thing I'm calling a Peterson hash. This is similar to Zcash's jub curve and hash. Perhaps some people have heard of this. What this is you take your secret input, you break it up into bits, and to each bit you assign some random curve point, and you have a running sum. Whenever you have a 1 bit, you add its corresponding curve point. If you have a 0 bit, you ignore it. And so your hash is just a sum of all these random curve points. And so here I've implemented this for 768 bits, and I ran this on my laptop before producing these slides. It took about 1 1/4 seconds to prove a pre-image of this hash. And we can see I've used 768 bits rather than 512. The reason is simply that in my current implementation, it's just as fast to verify anything from 512 to 768. So I put it as high as I could, since it wasn't going to cost me anything. But in future, we'll have fixed that, and it will actually be faster for 512 bits. So it took a bit over a second, I guess 1 seconds to prove. Then verification is 72 milliseconds, which is not great. Like 72 milliseconds for a single output. Well, this is even just one hash, and you generally want to do many hashes, do multiproofs and whatnot. That's not so great. But using this batch verification trick that I showed you guys for range proofs, this applies to circuits too, and now my Pearson hash here is only 5 milliseconds per additional hash. So if you have like 1,000 of these to verify, that's going to cost you 72 milliseconds for the first one, of course, but then the rest of them will just be 5 milliseconds per, so that's 5 seconds for 5 seconds plus 72 for 1,000 proof verification, which is cool. And as I mentioned earlier, the size of both of these proofs is about 2 kilobytes. I think the Peterson hash one is a bit under 2, and then the SHA-256 one is a bit over a difference in space. Okay, so I'm giving you guys these numbers for context to see that this is a practical zero-knowledge proof system. And I'm going to end by just listing a whole bunch of applications that I have, and this is very new. So we have a paper submitted to the IEEE Security and Privacy Conference. The final version is due in some number of hours, so this is really very new stuff. So all I can do is sort of try to share my excitement about it, find the time, which is not now because I'm running benchmarks for the paper. So range proofs, of course, is what I've been talking about. Merkle proofs. Well, proofs of solvency are a special case of this, where you take all of the Bitcoin outputs, you put them into a giant Merkle tree, and then you prove that you have some outputs that are in this giant Merkle tree, and also that those outputs add up to some amount you're claiming to have control over. Merkle proofs are more general. I mean, you could use this in principle to implement what Zcash does, where all the verifiers have this accumulator they're maintaining, and you would use Bulletproofs to produce proof that you are spending real coins that really exist of the amount that you're claiming you are. I think that with the circuits that we have implemented now, this would probably not be practical. Rather than SNARKs, which have a few milliseconds, it would be several seconds to verify these. One to 2 seconds, and then with batch verification, you get that down to a couple hundred milliseconds. But it's still not great, and it's still not practical. But there's a lot of work to be done reducing that. And for off-chain applications like proof of solvency, this maybe isn't such a big deal. Another fun application that I'll talk about briefly is multi-signatures with deterministic nonces. And here I have to get a bit more technical than I want to, but this is also a really important application. And in a lot of different interactive multi-signature protocols, there is a requirement that every party generate something called a secret nonce, which is like a separate key pair. It's like an ephemeral key pair that they're using just for the signature. And the signature is produced using some mixture of this nonce and their actual public key and whatever message that they're signing. And this extra public key is used to blind the original public key so that when they do computations with their secret keys, they have two. Remember from grade 9 that if you have one equation and two unknowns that you can't solve it, this will prevent anybody from learning anything. But it's critical that nobody ever use the same nonce twice in two different signatures. The reason being that if they were to reuse one, rather than always having a new variable for every new equation they add, suddenly they have a new equation without an extra variable, and now you have n equations and n unknowns, which remember is a solvable system. So they solve for all of the nonces anyone can solve, for all of the nonces and the private key, and now game over. So, in multi-signatures, every party does this, and there is there is an actual attack, in which one party starts the protocol, plays forward until the other one has produced a nonce and produced their part of the signature, then they go offline, they just go dead. And then they come back and they try to restart the protocol. And there's a standard way for generating nonces called RFC6979, in which case the honest person will generate the same nonce twice. But because they are working with some other counterparty who's contributing stuff to the message and into the sum of their nonces, rather than generating the same nonce twice for the same message, in which case it's okay, they'll just produce the same signature twice on different signatures with different hashes, and they will therefore reveal their private key to the person who's attacking. And the way to prevent this is either that both parties need to always produce random nonces, or both parties always need to produce deterministic nonces. Okay? If one party is allowed to vary and the other one isn't, then that's how this attack works. And there are many problems with random nonces, which is why people like this RFC 6979 thing. The problem is you need a reliable source of randomness. The source of randomness needs to not be biased, big things basically, and it needs to not repeat itself. You need to source some entropy from somewhere, which might be hard if you're some closed piece of hardware. So people like these deterministic nonces because it fixes all of these problems. You only need the randomness in your private key, and then you're good forever. So, if there was a way that every party could prove that they were generating their nonce deterministically, and they did not go offline, come back, and change their nonce, that's the critical thing, is when they come back, there has to be a nonce that's forced. 979, and then nobody goes forward with the protocol unless everybody has proved that they're acting honestly. That would be great, that would solve this attack. The problem is you can't really prove that you are generating your secret nonce honestly because your secret nonce is a secret. You can't reveal anything about it. You can't verify that it has any particular properties because any properties that somebody could verify just from the public data would be enough for them to, with Bulletproofs or with snarks or whatever zero knowledge proof, we can solve this. You can provide a zero knowledge proof that your nonce was generated deterministically. You can go, like in the last slide, you can run your message and your secret key and then all this good stuff through a SHA-256 circuit in a deterministic way, thus producing a what's called a de-randomized nonce, which is generated deterministic, and you can prove that. Every participant can prove that to every other participant. And now everyone knows that even if they just woke up from out of like one of Nick Bostrom's thought experiments and they have no memory of their previous interaction with the people they're interacting with, they know that those people are acting exactly as they did every other time. There is no possibility for them to have acted one way before and now be acting differently because they are providing a zero knowledge proof that they are acting in a deterministic way. And we can do this with Bulletproofs. Then there's another thing called scriptless scripts, which is what I talked about the last time I was here, maybe a year ago. This is the way to do all sorts of cool smart contracty things using digital signatures. And typically scriptless scripts exploit the linear properties of Schnorr signatures to allow very efficient, they can't tell what assets, they can't tell how many assets, they can't tell anything at all. And that's just done using an older form of zero knowledge proof called the Sigma protocol, which is very inflexible and quite a lot of specialized crypto development work to produce. You can do this now with Bulletproofs in probably a conceptually simpler way and even a more powerful way. It could be extended to allow all sorts of weird assets that somehow are functions of other assets. So I've thrown this word crypto derivatives there without putting any real thought into what that might mean. But if it means anything, it's possible with Bulletproofs. And I think that really should be the slogan for Bulletproofs, really. And that is it. Thank you.
So I will take some questions, of course.